So Kawecki resolves the conflicts, or as he sometimes calls them, the indifferences, between local planetary fields and the ever-expanding cosmic space by introducing his concept of variable warp density fields. Matter is condensed warp density. In Kawecki's theory, what we perceive as objective matter, like a planet or a star, isn't really a distinct entity at all. It's actually just a highly localized, extreme concentration, or you could say, a knot of this fundamental energetic warp density. This is basically his version of E equals mc squared. Matter is simply condensed space-time energy. Gravity, in this view, is the play of density fields. The so-called force of gravity doesn't come from the curvature of some objective geometric fabric. Instead, it's just the natural interaction, or the play, between these different density fields. A high-density field, like a planet, naturally creates a gravity well in the surrounding, lower-density field. The expansion of the universe, often referred to as Hubble's universe, can actually be seen as the massive general low-density field of the cosmos trying to equalize, or, relax from that initial high-energy distortion caused by the Big Bang. Not at all objective, the flexible nature of reality. This honestly is the most critical part of your question when we look at Kawecki's work. Subjective space-time. While standard physics tends to see space-time as having, an absolute structure, even if it's curved, Kawecki argues something quite different. He suggests that because space-time is actually an energetic density field, it's fundamentally flexible and, in a sense, subjective. Suspending mainstream laws. Kawecki contends that in the extremely low-density zero-point microgravity space fields that make up most of the universe, the typical objective laws of relativity, especially those equations that would predict infinite mass, just don't apply. And really, this flexible nature is what he claims would mathematically allow for faster-than-light space travel within a moving vessel, sidestepping the restrictions of Einstein's objective reality.
All right, let's dive straight into the big question. Is faster-than-light travel science, or just science fiction? First off, I want to be super clear. What you're about to hear sits way outside the mainstream. The idea that space could have a warp density, or that the laws of physics might just take a break in some special low-gravity zone, that's not accepted by the scientific community. Here's what we do know. Space isn't just an empty void. Thanks to quantum physics, we know there's energy everywhere, even in a perfect vacuum. That's called zero-point energy. Plus, Einstein's theory of general relativity shows us that space isn't static. It bends, flexes, even ripples. But, and this is a big but, the geometry of space-time is objective. That means the rules are the same everywhere, for everyone. And the speed of light? It's not just a speed limit, it's built right into those rules. You can't get around it just by tweaking how thick or thin space is, or by hanging out where gravity's low. So, as much as I love the idea of hopping on a warp ship and zipping across the galaxy, right now, faster-than-light travel firmly belongs in the realm of fiction. Of course, science is all about pushing boundaries. But today, those boundaries are holding strong. The speed of light remains undefeated. If you enjoyed this quick reality check, hit like and subscribe for more science. No warp required.
In the sunlit agora, Aristotle and his student pause beside a weaver's taut cloth.
Master, stones fall toward us, yet the far heavens seem to drift apart. Imagine there is only cloth. What you call stone or star is cloth tightly gathered. Dense gatherings pull upon looser threads, while broad, even regions slowly relax their strain. So gravity is knots following tension, and expansion is the cloth easing toward balance.